We're going to start our discussion of the different levels of the memory hierarchy by talking about probably what is the most apparent of them all, memory. It's the main memory, okay? So we're going to talk about a simple memory interface. Now, this simple memory interface, we're actually going to build from the ground up. Remember, what can you do with a single D flip-flop? Remember, we've got our data input, our clock input, and our Q output. And yes, that is a very, very small D flip-flop. Why? Because I'm going to put a few of them up here. So kind of just squint a little bit or picture what the inputs are going into that. So basically, we have a data going in. And if I make a couple more of these, D, clock, Q, data going in, because, you know, we probably don't want to store just a single bit. You know, when we were designing those state machines, yeah, that made a lot of sense to just be able to store 2, 3, 4 bits. But whenever we're talking about code, we need to store a little bit more than just a single bit, right? So I got 6 there. How about I make an 8th one, 7th and 8th one like this. There we go. Now each one of them has its data input. Now, when they come from the processor, and the goal is this, that the processor says, I got a byte I want to store. How does it do it? Well, it puts it on these data lines. I'm going to label these D7 down to D0, all right? And so that came out not looking like a 0 at all, did it? And so, whenever you're looking at this, the very first step when the processor wants to store something to memory is to say, okay, here's the value I want to store to memory. The next thing that happens is somehow we've got to trigger or clock in that data. And so we've got a single line that we're going to connect to all of these guys. All right. And that clock line, and I'm going to have to move that because I got a little bit more circuitry that I want to put on here. But basically, I've got this clock line, right? And in fact, I'm going to call this clock sub 0. So, step 1, processor puts data on these data lines. Step 2, pulse that clock, store it into all the flip-flops, right? Well, that takes care of storing. But what about reading? Well, reading, what we're looking at is we have to figure out what's inside each one of these D flip-flops, right? And the way we do that is that we grab it from the Q. Now, something that's going to become apparent when we have our discussion about this system is that if we have a different set of lines for storing data than we do from reading data, we've doubled the number of data lines. Like, for example, right here we have 8 data lines. If I want one set of data lines for storing and one set of data lines for reading, I'm going to have 16, 2 times 8, 16 data lines for reading and writing. And the idea is that, you know, we really don't need to have, they're not both being used at the same time. Either the processor is storing data, we call it writing data, or it's reading data. So why don't we just use the same set of lines the same sort of external pins, the same sort of connections to the processor for reading and for writing. And so these Q lines, and it's going to have to go through a little bit of circuitry here, making it so that you can actually connect either to the D's or read from the Q's. And so each one of these makes it so that each one of the data lines becomes what we call bidirectional. All right. And so all those Q's go back into the data lines. And that way, when the processor is trying to read data, it's going to have circuitry in the memory which switches those data lines so that they become outputs from the cues. When the processor wants to write data, its circuitry inside the memory is going to switch those data lines so that they're inputs to the Ds. All right. Now, how is that circuitry going to be controlled? Well, it turns out that that circuitry is controlled with two very simple lines, and I don't know if I'm going to have a whole lot of room over here, but I'm going to put one of them here, and this is going to be R bar, and the other one I'm going to put down here is W bar. All right, so let's do a little truth table based on R bar and W bar. Now, hopefully you remember from our discussion a long time ago in a previous lesson about the bars over inputs. And the bars over inputs identify them as an active low signal. In other words, stuff happens when the signal is a 0. The signal is basically idle or not activating anything when it's a logic 1. So if I go through all of my possible combinations for R bar and W bar, it gives me every possible condition for these two control lines to be controlling the direction of the data lines. And so the way it works is this. And I'm not going to look at the top line just yet, but if we've got a 0 on R bar and a 1 on W bar, that means the processor is reading data. All right. All right. So let's take this a step further. We'll figure out these processes, these steps to interfacing between the memory and the processor. Step 1, the processor puts a 0 on R bar and a 1 on W bar. These are both connections or controls that are coming from the processor. The processor puts a 0 on R bar, a 1 on W bar. That makes it so that the circuitry connects all the cues to the data lines. Then the processor identifies, well, we'll talk in a minute about the identification, but it selects that row of latches, of flip-flops, and it reads the data bits. All right. Now, what if it wants to store data? Well, if it wants to write data, it puts a 0 on W bar, a 1 on R bar. So the processor, in this case, is writing data, right? What about these other two cases? Well, those are a little bit special, right? This bottom case, 1 on both R bar and W bar, means that the data bus is idle. It's not passing data back or it's not passing data from memory to the processor or vice versa. This 0-0 condition is not legal. It is illegal. We don't want to allow that condition to occur. All right. So I can store a byte. Storing a byte doesn't really do much for us, does it? And by the way, as a real quick side note, I've done a lot of these interfaces. I've worked with a lot of the low-level processor stuff, and the vast majority of memory stores individual bytes. And you think, okay, but I've got a 32-bit processor. I'm storing 32-bit integers in my memory. Well, how do I do it whenever I've only got 8 bits? Well, I need additional memory locations. I need more of these rows. After making a little bit of room on the board, let's make some more of these memory locations and see how all that works. Now, I've been doing this stuff for a while, and in all of my classes, this is the one part of the on-the-board activity that tends to take a little time. Probably really cool that we're watching this with a video rather than watching me in real time. Well, that was easy enough. Let's see what's appeared up here on our screen, on our board. First of all, as I said before, we're not looking at storing 1 byte. We're looking at storing billions of bytes, right? So whenever you hear about a 4 gigabyte memory, what you're talking about is 4 billion, more than 4 billion, whenever you think about the powers of 2, 4 billion of these rows, all right? Now, think about, we're just going to do storing data right now because there's a little additional circuitry that will be needed in order to read it. But in general, what you're looking at is I've got signals that are going to activate each row. So if I want to store data, processor first puts the data values that it wants to store on those 8 data bits, right? On those 8 data lines. Then, since it's storing, writing, we need to put a 0 on W bar and a 1 on R bar. And then it needs to pick exactly one of those lines to activate, exactly one of those lines to put a pulse on in order to store it in the correct row. And similarly, the process, and it'll be a little bit different because instead of writing to the D inputs of the D latches, now we're going to be reading from the Q outputs of the D latches. What the processor will do is it'll put a 0 on the R bar, saying that it wants to read data, a 1 on the W bar, and then it'll select exactly one of these rows in order to get all the Qs connected to the Ds so it can read. All right, now think about this. We've already saved some pins, some of these connections, by combining the writing data with the reading data. And by just adding these 2 control lines to say what direction. Are we sending data in, writing? Are we reading data out, the reads? All right, but this is just an 8-byte memory, only capable of saving 64 bits. What are we going to do whenever we try to make a bigger memory? Hey, let's just keep it really simple, a really small 1 meg memory. 1 meg is going to have 1 million of these clock lines. Not feasible whenever it comes to physical connections to the memory. So how are we going to take care of this? Well, we add a little circuit here that inputs or controls which one of these clock lines is going low. Now, remember, only one of those clock lines is going low at any one time. So what we really want is something that's going to say, okay, in this particular condition, we want exactly clock 0 to go low. In this particular condition, we want exactly clock 1 to go low. So this circuit that we're going to add right here, I'll just go ahead and put this here, kind of push me out of the way, is going to be a circuit that will drive these clock lines. And this circuit is referred to as an address decoder. Now, in one of the lessons, we talked a little bit about the decoder circuit, and the decoder circuit says for a very specific pattern of 1s and 0s, we are going to make a signal on the output. And what gate did we use? Well, we used an AND gate, right? Unless it was an active low decoder, and if it was an active low decoder, we used a NAND gate. And remember, the NAND gate goes to a 0 for exactly 1 pattern of 1s and 0s at its input. Now, the circuit we're going to do here is going to take 3 inputs. And I'll tell you why I picked 3. The reason I picked 3 was because I have 8 clock lines here. How many patterns of 1s and 0s can 3 bits take on? Well, 8, 2 to the 3, right? 0, 0, 0, all the way up to 1, 1, 1. And so what I want to do is have, when I have a 0, 0, 0 here, I want to put a pulse on clock 0. When I have a 0, 0, 1 here, I want to put a pulse on clock 1, all the way down to when I have a 1, 1, 1 here, I want to have a pulse on clock 7. Once again, these are just decoder circuits. And if I want to make them active low, I'm going to make them NAND gates. So let's do that. Let's just go ahead and drive each one of these clock signals with an independent NAND gate. And what this is going to give us is the ability to put a pattern of 1s and 0s on these 3 input lines that will trigger exactly one of the clock lines, because we are only going to be interacting with 1 memory location at a time. There's no reason to store the same value to 2 memory locations, right? And when you try and read from 2 or more memory locations, you get something called bus contention, where all the 1s and 0s are battling with each other to see who wins, and in the end, nobody does. It's just garbled data. So we're going to have exactly one of those signals going low. Now, I am going to name these signals. I'm going to call this A sub 0, capital A sub 0, capital A sub 1, capital A sub 2. And these are corresponding to a 3-bit number, a 3-bit address. So I'm going to, from the processor, I'm going to pass 3 bits. One of the least significant is A0, then the middle one is A1, and then the most significant one is A2. Sorry that didn't come out all that clearly, did it? So for clock 0 to be pulsed, what I need is 0, 0, 0, okay? Now, for clock 1 to be pulsed, well, clock 1, that's going to be a 0, 0, 1. So A2 is going to be a 0, A1 is going to be a 0, but A0 is going to go straight in. Clock 2, that means I want to put a 0, 1, 0, the decimal or the integer value for 2. And that 0, 1, 0 is going to have a 0 on A2, a 1 on A1, and a 0 on A0. Clock 3 is going to be 0, 1, 1, so that's going to be 0, 1, 1. Clock 4 is going to be 1, 0, 0, so that's going to be 1, 0, 0. Clock 5 is going to be 1, 0, 1. So that's going to be 1, 0, 1. Clock 6 is going to be 1, 1, 0. So that's going to be 1, 1, 0. And then clock 7 is going to be all 3 of them are 1. So 1, 1, 1. All right, and make sure I get my dots showing up there, okay? And there you go, a board full of circuitry. Not a whole room left for the instructor. But let's talk about this process. So we've built the process just a little bit more. The process goes something like this. If the processor wants to store data, it puts a pattern of 1s and 0s here that it wants to store. It puts a 0 on W bar so that it does the write operation, and a 1 on the R bar so it's not doing a read operation. And then let's say it wants to store to row 6. It puts a 1, 1, 0 on my address lines, and the address lines select that line to clock in and stores the data. Now it's a little bit more complicated than that, but in general, that's what you're looking at. You have these lines coming from the processor, outputting address, identifying which row we want to store in. Inputs and outputs bidirectional, connected to the data lines, which allow data to pass back and forth, and then outputs from the processor to control whether we're storing data or whether we're reading data. Now it turns out there's one more signal that we need to have or add to our memory device here. And that one more signal is something called a chip select. Now the reason for this is because no processor or no computing system has just a single memory. For example, you may have heard of this thing called a BIOS, right? And a BIOS is a certain type of non-volatile memory that allows the processor, whenever it first powers up, to find code to execute right from the get-go. That is different than this randomly accessed memory, the volatile memory, where our programs and variables are being stored. So there, right up front, there's two different memory devices. But also, there are different input and output devices, such as a network interface card or a graphics card, that pretend to act like memory. So they use exactly the same interface too. And so all of these devices using this exact same interface are communicating to the processor over the same data lines. Well, That means we need to have an additional mechanism on these memory devices that allows us to determine which one of these devices am I talking to. Am I talking to the BIOS? Am I talking to the graphics card? Am I talking to main memory? Am I talking to the network interface card? Which one of these devices am I talking to? Because if I've selected, for example, the network interface card to communicate through this mechanism, well, everybody else has got to be deaf. It's got to be completely off the lines. We call that high impedance. What they do is they electrically disconnect their data lines so they don't participate in the conversation that was meant only for the network interface card. That means we have one additional signal. And I don't really have a whole lot of room to put it in here, but I'm going to try. How about we put it in here with the reads and the writes? There is one more signal that is also active low that is identified typically with like a CS. That one says CS. That stands for chip select. So we've got chip select. Now, it goes by other names too. For example, it might go by the name chip enable, or if it's a device that only outputs, in other words, you can only read from it, you can't store to it, it might be called output enable. So there are all sorts of names that you might see this chip select going under. But in general, what you've got is a signal, active low, that when it's a 0, connects my memory to the processor. When it's a 1, it makes it so that memory device disconnects itself from the processor and does not participate in any of the conversation that the processor is trying to have with another memory device. All right? Now, to give you an idea that I'm not making this stuff up, I went to the web and just did a real quick search on static RAM. In the old days, we used to design these directly into our circuit and solder them onto the board. And this is one of those old style memory devices. If you look at this diagram right here, in the upper left-hand corner, you'll see what looks like a large O. That is actually a small divot that is in the plastic on the top of the chip to identify the starting pin, pin 1 for this device. You can also identify it with the little notch that's at the top of the chip. These two identifiers are all that you actually see physically on the outside of the chip. The pins are numbered. Those numbers don't appear on the outside of the chip, but they are used to reference what connections each one of those pins make. So for example, pin 14 is ground, that's 0 volts, and pin 28, that's VCC, typically 5 volts on a device like this, in order to power the chip. Now, some identifiers that you may not recognize right away, but I'll explain them to you, are those I/O, the 0 through 7. Those are the 8 data lines. Just so happens that the data sheet that I found this on identified those as input and output rather than data. Those are bidirectional. They go both in to the chip and out from the chip. The other lines of importance are A0, which is on pin 21, A1, 2, 3, 4, which are on pins 23, 24, 25, and 26 respectively, and then 5 through 14 on pins 1 through 10. Those are our address lines. And if you think about it, those 15 address lines give us 2 to the 15, or 2 to the 10 times 2 to the 5th, which is equal to 1K times 32, or 32K memory locations. But you look at that title, it says 256K. Well, it's actually telling you how many bits are in there, not how many memory locations. You divide 256K by 8, you get the 32K memory locations, each of which is identifiable with a different pattern of 1s and 0s placed on A0 through A14. A0 through A14 are all inputs into this static RAM. They come directly from the processor and are controlled by the processor in order to reference what memory location the processor wants to communicate with. There are 3 other pins of importance here: WE, OE, and CE. Well, those are not the names that I used whenever I described this on the board, but they are the names that are used for this particular chip. WE is just write enable. That is the W bar signal that I used. I used the more generic symbol. Then OE is output enable or read, R bar. And then CE is the chip select. All three of those are active low, and they're of course used to interact between, to control the interaction between the processor and the memory device. So in our next lesson, we're going to dig a little bit deeper into how those chip selects work so that I can show you exactly how multiple memory devices can communicate with a single processor.